Okay, so we're going to continue now with question 4.3, which is another isothermal process, but unlike question 4.2, we are going to use the ideal gas law the ideal gas equation of state to solve the work integral. So a piston cylinder device initially contains 0.3 kilograms of nitrogen at 130 kilopascals and 190 Celsius. So we have to convert that to Kelvin at some point, which is now allowed to expand isothermally to a final pressure of 75. Compute the boundary work in kilojoules. Okay, so again, just a few notes. We see we're expanding. We're going from high pressure to a low pressure, right? Since we're expanding, the volume is definitely going to increase. That means we're doing work we're outputting work again, so we're expecting a positive number. If we get a negative number in the result, that means something's gone horribly wrong and we've made a mistake. So just keep that in mind. And again, this is an isothermal process, and unlike the last time, as mentioned, this is an ideal gas, so the way we go about solving that integral will be a bit different. This is not, like last time, an isobaric process, because the last one was sort of isothermal and isobaric. This one is just isothermal. We can't solve the integral by just doing PV2 minus V1. So enough talk, I'm going to actually do this now. So we just have to find the work. So let's start from the most basic way we can do this. Work is the integral from 1 to 2 of P dV. Great. Now we can't just pull out we can't just pull out P like last time because pressure is not constant. The question itself tells us. I'm just going to plug in my other thing. 1 second. Sorry about that. The question tells us that the pressure is going from, I think it was like 150 to 75. It's changing. So we can't, it's not a constant, so we can't just pull it out. But what can we do? Well, we can use the ideal gas law because this is nitrogen. We're assuming it's an ideal gas. We can use the ideal gas law, which is PV equals mRT, or alternatively, P equals mRT over V. And this is R specific, which we'll have to get from a property table. So it's dependent on the fluid. But anyways, if we plug this in here, let's see if that can help us. Surprise, it can. Spoiler alert. mRT dV over V. Sorry, these should have strike throughs. Great, M is the mass. We know that that's a constant, so we can pull that out. R is also a constant, I just said. And the definition of this process, it's an isothermal process, so temperature is also constant. So we can do this. Work equals mRT times the integral, and we're left with dV over V. So from just calculus, we know that the work of such a process will be mRT ln of V2 over V1, like this. So pretty simple. Now, in terms of the actual values that we're going to pop in here, so we're told that the mass is 0.3. Now, R, well, I don't know what it is, but I'm going to find out very quickly by going here to the property tables. And I believe this was for nitrogen. So if we go, there we go, we're looking for nitrogen. R is this like third column here, 0.2968 kilojoules per kilogram Kelvin. Let me just make sure that it was nitrogen. I can't really remember now that I say it out loud. Here. Yeah, nitrogen. Sorry about that. So 0.2968 kilojoules per kilogram Kelvin. So 0.2968. And because this is in kilojoules per kilogram Kelvin, we're expecting our answer to be in kilojoules, not joules. Temperature, we are told, is Let me just check it. I keep forgetting. Temperature is 190 and it's isothermal, so that's constant, but we of course have to convert Celsius into Kelvin, and then it becomes 463, and that's by adding 273. So 463 ln of V2 over V1. Bit of an issue here. We don't explicitly know what V2 over V1 is. So we have to first find the volumes directly from the ideal gas law, but we have enough information to do that in both states. So what we can do before we continue, we'll do this on the side here, is we have to do V1 equals MRT over P, right? We can see that from here. If we isolate V, it's just MRT over P. So where M was 0.3, R is 0.2968 kilojoules per kilogram. Sorry, 0.3. 0.2968. Temperature we saw was 463. And we'll divide by the pressure, which initially the pressure is, oh, that was it right there, 130 kilopascals. So that will give the volume will be 0.317 meters cubed. And if we do the exact same thing for V2, noting, of course, the pressure has now changed to a value of 75. So with a value of 75, we just get 0.3 times 0.2968 times 463 divided by 75, and we get 0.54, well, 55 really. 0.55, I'll just draw this because it's the same equation, just a different pressure, 0.550 meters cubed. So now we can actually do this. So it's V2 over V1. And if we do this, what will we get? 0.3 times 0.2968 times 463 times ln of 55 over 31.7. And that gives us 22.72. And remember, because this is in kilojoules per kilogram Kelvin, this answer will likewise be in kilojoules and not just joules. So in answer to the question, the work done by the system, which is positive, so we're happy that checks out, is 22.72 kilojoules.